So we've learnt that nuclear fusion is not actually a very plausible energy source for one of these things. You just produce so much iron and you don't know what to do with it. If it stays in the middle, you get a black hole, and a star with a black hole in the middle is not going to shine for very long. If you squirt it out, it makes an impenetrable curtain. So most likely we need gravity, and that means a very big black hole.
So let's think about what these things look like if we look at them in the nearby universe. So here's a picture of a nearby galaxy, one of the nearest by galaxies that has one of these quasar type things in them. And you can see that in the middle, where it's shining, is right in the middle of a normal galaxy. We also know that galaxies, the centers of galaxies, seem to have evidence that there is really high mass concentrations consistent with millions of solar mass black holes.
So let's zoom in on the centre of this for the Hubble Space Telescope image. What you can see is an incredibly bright dot in the middle. This is the quasar, if you like. And it's got almost two cones up and down of illuminated, in this case, yellow light. What's happening here is the intense ultraviolet radiation from the quasar is coming out, but only in two cones, like searchlight beams up and down, and zapping the gas in the galaxy and making it fluoresce and glow very brightly.
So if we go in and zoom in even further on, in this case, a different object, but a similar type of object, with the Hubble Space Telescope, we can see that you see the central source. In this case, it's not very bright, and that's because there seems to be a lot of junk around it. And this junk, we think, is dust, gas, and optical light, of course, is absorbed by dust and gas, but radio and X-ray, not so much. So that might be why some of these things are really bright, the radio and X-ray, and we can't see them in the optical.
Yes, that was some of my own research back in the 1990s, showing that in fact for every quasar we can see, there are another 3, 4, 5 we can't see because they're hidden behind this cloud of dust. So if you look down from the top or the bottom, that's where the radiation is coming out, we can see a quasar. If you look from sideways, we don't see a quasar at visible light wavelengths. You don't see anything at all at visible light wavelengths, except maybe the galaxy. What you instead see is only X-rays and radio from these things. But let's now zoom right in closer still. I've put together a simulation of what it would look like if you were actually here to the naked eye. So this is showing true colours. Of course, if you actually were here looking with the naked eye, you'd be vaporised in milliseconds. So let's imagine you've got some really good sunglasses. Out here, this purple light is due to gas once again being zapped by the radiation. And as you get towards the centre, you see, we believe, a spinning disk. It takes many hours to spin, so if you were actually there, you wouldn't see it moving. Hotter and hotter as you get closer in towards the centre. The idea is that the gas is swirling around the black hole in the middle, and the inner bits have to swirl really quickly for centrifugal force to balance gravity. As you go further out, they can spin slower, which means you get viscosity rubbing between the inner and outer bits, and that makes it very, very hot. That liberates the energy. As you go right into the centre, you're getting temperatures up to maybe about 100,000 degrees, which is why it's emitting this incredibly blue colour. But then, when you get to about 3 times the Schwarzschild radius. The Schwarzschild radius of a black hole is the radius of no return, beyond which you have to go faster than light to escape. That's actually about this size in this diagram. But when you're within 3 times that, there's no such thing as a stable orbit. So the gas spirals into, gets here, and then it falls into the centre rather rapidly. And in the middle, about that size is a black hole. It's black against black, so you can't see it in this diagram. So that's what we believe these quasars would look like if you were up close to them and had really good sunglasses.